Hello everyone, my name is Áron Holló, and in this video my teammate and I are going to present our homework for traffic modeling, simulation and control subject. Our initially chosen topic was changed and the new topic is hotspot detection of Gyöngyös city's road network. We were advised by our supervisor that we should focus only at the city center and not on the bypass roads and the outskirts. On the left image, we can see a bird's eye view of the road network of Gyöngyös. And on the right side, we can see an image of this network from the simulator with the generated traffic. Our goal was to find the hotspots of the city center under different traffic loads. Our method can be divided into 4 areas. First, we selected different road lanes, more specifically 15 road lanes in the city center for our investigation. Then we selected a macroscopic traffic variable, the so-called density, and calculated it on the selected road lanes to measure the traffic volume. Thirdly, we made several diagrams to visualize the evolution of the traffic in real time and to be able to get quantified feedback during the simulation and not only just a few but all the selected road lanes at once. And in the last step we proposed an additional summary diagram that can be used after the simulation to summarize the whole simulation process and get an overview of the propagation of the traffic.
Hello everyone, my name is Tóth Tibor Áron and I will talk about a few other aspects of our solution. As my team member Áron said, we started our solution with a lane selection. We investigated 15 lanes in the downtown of Gyöngyös. We had 2 policy for the selection. One is that we want to check easily the lanes which are near to each other. So nearby lanes are indicated with numbers close to each other. The other is that we wanted to differentiate main traffic input sources. Therefore, we grouped lanes into 3 categories based on their directions, as you can see on the figure on the right side. In real time, we are measuring the traffic density of each lane, which is the number of vehicles divided by the length of the lane. Based on this quantity, we are able to measure directly the traffic load on the lane and detect hotspots. We propose several feedback to the user about the state of the traffic. One is the in-simulation vehicle coloring. This is basically coloring those vehicles blue which are standing on a lane with density higher than 70%, and coloring vehicles to red when lane density is the maximum among all of the inspected lanes.
On this slide we can see a recording from one of the simulations and we can see the red numbers for the selected road lanes. The changing colors can be seen of the vehicles because at each step the vehicles on the most dense lane from the observed roads turns to red, and where the density is above 70%, the vehicles turn to light blue color. All other vehicles will keep the yellow color. On the left, above the network, the current step can be seen, and we are around 2000 right now, and we simulated each time for 2500 steps. On the right side, we can see 2 real-time diagrams related to density. On the bottom one, we can see each observed road lane's current density values as the simulation propagates. If we select a road lane number on this diagram, then we can match its color to the top diagram, and we can see how the density changed of this road lane in the last 100 steps. The colors of the bar diagram and the line diagram match each other, so it's easier to pair them. And if we take a look on some road lanes in the simulation, we can see the density values of them with the diagrams and compare them to other road sections which we don't see at that moment. As we were advised, our focus was mainly on the city center, but later in the video, or at the moment here right now, we can see that intersection 5, 6, 7 and 8 has some serious problems with the traffic volume in this simulation, which had 1.5 times more traffic. This certainly has some effect on the density in the city center as vehicles get stuck in the outskirts. On this slide we can see the density change throughout the whole simulation from each observed road lanes. On the left side we had the original volume of traffic, and on the right side we had twice as much. The selected road lanes handle the original traffic with no gridlocks, while with 2 times of the original traffic load, several lanes reach high or maximum density pretty soon, and towards the end almost 2/3 of the road lanes reach maximum density, and the vehicles get stuck, as it can be seen on the simulation.
During our evaluation, we recognized a few observable patterns of jam formation in the city with our proposed tool. On the left side, we can see how the jam is spreading if one of the inner lane, in our case lane 1, is jammed. The traffic is stuck at step 396 on lane 1, and after around 200 simulation step, the lane 2 is starting to jam. This is because a vehicle from lane 2 want to drive in the direction of lane 1, which is fulfilled with stuck vehicles. The other pattern is on the right side. Thanks to our lane numbering and grouping, we can recognize different traffic flows from each direction of the city. On this particular figure, with the help of the hand approximated density distribution of each groupings, we can recognize a high traffic load from first direction of the city. Finally, I would like to summarize our work. We created a real-time hotspot detector and monitoring tool for Sumo Simulator with Tracy. We tested our tool on city of Gyöngyös, and we proposed a summarized evaluation result and some observable patterns of traffic behavior. All in all, we want to thank the support of our supervisors during the work. On behalf of my team member and myself, I would like to thank you for your attention.